Okay, so for these two examples, we're going to be verifying the identity. Starting with this example, we have cosine to the fourth theta minus sine to the fourth theta equals cosine squared theta minus sine squared theta. We want to, again, always try to simplify the more complicated side. Generally, it's easier to take a complicated thing and simplify it down than to make a less complicated thing more complicated. So looking at these two sides of the equation, they look very similar, but notice this side has exponents of 4, whereas this side has exponents of 2. So this side is going to be a little bit more complicated to work with. So using this side of the equation, we need to find a way to simplify it to what we have on the other. If we look at this, it's not very apparent right away what we can really do with this. But there is a little bit of a trick. If we, I'll write this off to the side, have a squared minus b squared, we can factor this. This is a difference of squares formula. This will become the square root of the first term, a, minus the square root of the second term, b, times the square root of the first term, a, plus the square root of the second term, b. So whenever you have two perfect squares being subtracted, you can factor them using this formula, which is the case here. The square root of this first term, cosine to the fourth theta, is cosine squared theta. And the square root of the second term, sine to the fourth theta, is sine squared theta. So using this formula, with a being cosine squared theta and b being sine squared theta, we will get cosine squared theta minus sine squared theta times cosine squared theta again plus sine squared theta. And at this point, notice we have matching values here. The only difference is this cosine squared plus sine squared. And that might seem a little bit odd how we could have the exact same thing on each side of the equation, but this entire extra value being multiplied on. But notice this is a Pythagorean identity. Cosine squared theta plus sine squared theta is equal to 1. That's always true. So this can be substituted out with 1, giving us cosine squared theta minus sine squared theta times 1. I'm going to switch markers here. And now anything times 1 is itself, so we get cosine squared theta minus sine squared theta on the left, with a square here, is equal to cosine squared theta minus sine squared theta on the right. That means this identity has been verified. Now with that, let's go ahead and try the next example. This one is a bit more difficult, but go ahead and take a moment, pause the video, see if you can try to figure out which side is more complicated and that you could simplify down to get to the other side. Okay, from here, it actually turns out in this case, it's very hard to say which side is more complicated. In the first side, you have a fraction just like the other, but over here, you have a lot of terms in your numerator, and you have exponents, versus over here, you just have regular terms that are not being raised to a power. But my suggestion would be to work with this side. The reasoning for that, there are certain factors that really tell you whether or not a side is more complicated. And typically, if you see secant, cosecant, tangent, cotangent versus sine and cosine, that is a sign that you have a more complicated side. Another factor is, do you have more trig functions? Here we have 4, here we have 3. So if we use this side here, we're going to try to start changing it, manipulating it to become what we have over here. So notice the first thing is we don't have any of our normal cues. We don't have a Pythagorean identity. We don't have multiplication or division. So our best bet here would be to change everything to sine and cosine to see if something looks like it will cancel out to be easier for us to work with. So secant of alpha is the same thing as 1 over cosine of alpha. Tangent of alpha is sine of alpha over cosine of alpha. Secant of alpha is 1 over cosine of alpha again, minus tangent of alpha again is sine of alpha over cosine of alpha. And now it's a little bit more apparent how we can approach this problem. Every one of these inner fractions has a cosine of alpha. So if we multiply the numerator and denominator by cosine of alpha, it won't change the problem because we're multiplying it to the numerator and denominator. We're also not affecting the other side of the equation, which is perfectly okay. So when we distribute this to every term, the cosine alpha in every single denominator is going to cancel out, leaving us with 1 plus sine of alpha over 1 minus sine of alpha. And it might not seem like we're getting much work done here, that we're getting any closer, but notice now in our numerator we have sine, which is what we need. So we are on the right path here. And the trick to this problem, a key step that can come up when you are verifying identities, is that sometimes you need to multiply the numerator and denominator by a conjugate. So in this case, we have 1 minus sine of alpha in the denominator. Let's see what would happen if we multiply the numerator and denominator by its conjugate. When we do, in the numerator, we can distribute all this out, which gives us 1 times 1 is 1, plus 1 times sine of alpha is just sine of alpha, plus sine of alpha times 1 is sine of alpha again, plus sine of alpha times sine of alpha is sine squared alpha, over the denominator. When we multiply all that out, notice we have one term minus another, and then the same term plus another. And they are matching. This is our difference of squares formula again. We're going to end up getting a squared minus b squared. We'll actually show that written out, but this is why we wanted to multiply by that conjugate. We're going to get 1 distributed to each of these terms and sine of alpha distributed to each of these terms. That gives us 1 times 1 is 1, plus 1 times sine of alpha is sine of alpha, then negative sine of alpha times 1 is minus sine of alpha. And negative sine of alpha times sine of alpha is negative sine squared alpha. Which when we simplify the numerator, we get 1 plus sine of alpha plus sine of alpha. Those are like terms. They'll combine to give us 2 sine of alpha plus sine squared alpha. And then in the denominator, the sine of alpha minus sine of alpha are like terms. They're going to cancel each other out, leaving us with 1 minus sine squared alpha. Again, that is our difference of squares formula in action. 1 minus sine of alpha times 1 plus sine of alpha is 1 minus sine squared alpha, which you could then factor back to get to this. And notice we are almost completely there. The numerator is completely matching. The only difference is the denominator. We have 1 minus sine squared alpha. We need cosine squared alpha. But this is a Pythagorean identity. Cosine squared alpha plus sine squared alpha is always equal to 1. So we can substitute that into our problem by manipulating it. We need 1 minus sine squared alpha, so if we subtract this sine squared alpha from each side off to the side of all of our work, we get cosine squared alpha is equal to 1 minus sine squared alpha. And this is always true because it came from our Pythagorean identity, so we can substitute it into our problem. 1 minus sine squared alpha is going to equal cosine squared alpha, which gives us 1 plus 2 sine alpha plus sine squared alpha over 1 minus sine squared alpha is cosine squared alpha. And that is exactly what we needed on that left side. So we can rewrite the left side. And this is now verified.